So this is chapter 8, which is to deal with systems of equations and matrices. So as kind of an introduction, what we're doing here is we're basically trying to not automate, but come up with a logical series of steps to solve multiple linear equations. So we did this in algebra or algebra 2, but let's say you have two equations. And two unknowns. And graphically speaking, the solution of these two equations is the intersection of the two lines. So I don't know what they look like, but let's just assume that. So this is the x value, this is the y value. So in 2 dimensions, you can think of it as the intersection of two lines. In 3 dimensions, if you have x, y, and z, you can think of it as the intersection of 3 planes. But what we did, we had 2 main procedures that we learned in algebra. One was substitution and one was elimination. And what we're doing here is more like the elimination. So what we would have done is we would have taken the original equations, say we keep the first equation the same, and then we would take the second equation and multiply by some number such that we can eliminate one of the variables x or y. So we would take this row and we'd multiply it by -3. So -3 times x would give you -3x. -3 times -15y would give you +15y. And -3 times 5 would give you -15. And then you would add the two equations. So when you add these two, you eliminate that variable, and you'd end up with 17y. 2 plus 15 is 17y is equal to -5. And then you would divide both sides by 17. You get -5/17. And then you could plug this number back in to, say, this second equation. So if you solve the second equation for x, you get x is equal to 5y plus 5. So I move this to the other side, it becomes positive. And then you'd plug in your value of y, which would be -5/17. You'd add 5. And then -5 times 5 is 25, so I get -25/17. And I convert this to 17ths. So 5 times 17 would be 85. So 5 is the same as 85/17. You add the two numerators together, you get 60/17. So that would be my x solution, which would be the x coordinate of the point of intersection. This would be my y solution, or my y point, my y value, this intersection thing. So what we're doing in matrices is we're trying to do that kind of operation, but we're going to take things like multiplying rows by factors, but we have a certain process which have names. They're called, well, the multiplying and subtracting and things like that are called elementary row operations. The Gaussian elimination with back substitution and the Gauss-Jordan elimination, those are ways for solving for the unknowns. Now, to represent this equation that I referenced here earlier in a matrix form, you have 3 matrices. One matrix which involves the coefficients associated with x and y. So we'd have 3. 3 would be associated with x. So this would be like my x column, this would be my y column. So the y would be 2. In the second equation, x is, the coefficient in front of here is 1, and the coefficient there is -5. And then you have another matrix which just consists of the two variables, x and y. And then you have the right-hand side, which is 10 and 5. And so this is just a shorthand way, or a different way of representing this same information. And the way you do matrix multiplication is you take this 3 times x and 2 times y, and you add them together to get that, and that equals that value. And then you take 1 times x and negative 5 times y, and that equals 5. So it's just a shorthand way of representing the equation. Now, to get the solution, what you do is you create what's called an augmented matrix. And augmented means that you take one matrix and you add the other matrix to it. So I take this matrix and I add those two values in that column. So I end up with a matrix. This is what we would call a 2 by 2, and it's always the number of rows by the number of columns. This is a 2 by 2 matrix. This would be a 2 by 1 matrix, 2 rows, 1 column. This would be a 2 by 1 matrix. This would be a 2 rows and 3 columns. So it'd be a 2 by 3 matrix. And sometimes we draw a little dashed line to separate this, to kind of delineate between what part is the coefficient matrix and the right-hand matrix. Now, ultimately, to solve for either x or y, what we do is we do different elementary row operations. So what does that mean? Well, you can, one elementary row operation is just to multiply or divide a row by a constant. So, if I multiplied this row by 3, I'd take everything and multiply it by 3. And if you do these row operations, you can substitute a given row with the modified row. So let's see, if I multiplied the first row by 3 and just left the second row the same, I'd have 9. So 3 times 3 is 9, 2 times 3 is 6, 10 times 3 is 30. And I'd end up with this modified matrix. Now, the solution for this matrix is going to be the same as the solution for the original matrix. So by doing these, I come up with a different matrix, but I still have the same solution. What this matrix would represent is 9x plus 6y is equal to 30, x minus 5y is equal to 5. And that compares with the original equation. Find my equation here. So here's my original two equations. Where the heck are they? They're right here. And the only difference is the first row is 3 times larger than the original row. So I'm just multiplying by a common factor, so it doesn't change the solution. It just scales it. The second one is to add or subtract one row from another. So that's just taken. So what I could do, say, example of that would be if I'll keep the first row the same. So it's 3, 2, and 10. If I just, let's say, added the first two rows together. So I add 3 plus 1 is 4, 2 minus 5 is negative 3, and 10 plus 5 is 15. So it turns out, again, this augmented matrix represents an equation, and the solution for these two equations is the same as the solution to this equation. So you can just add rows together You add the x parts, the y parts, and the constant parts. You can also add or subtract a multiple of one row to another row. So let me give an example of that. You know, I could, let's take the second row and leave that one the same. So you're going to leave this. And if I took that row and I multiplied it by 2, 3, let's say add 3. Well, let's actually multiply it by -3. So we're gonna multiply this row by -3. So you get 1 times -3 is -3. -3 times -5 is 15. -3 times 5 is -15. And then I'm going to add that to my first row. So I take a multiple of one row and I add it to the other row, which is my first row. So I add these coefficients in the row and I get 0, 17, -5. So what I can do is I can substitute this new row with the original row. So I took the second row, multiplied by some constant factor, so I take this times -3, I get that. I add that to the first row of my matrix, and the resulting row I can substitute. And again, the solution for this system of equations is the same as the solution for this system of equations. And I guess the final one is you can switch rows. You can't switch columns, but you can switch rows. So an example of that would be you can just take row 2 and make it row 1, and take row 1 and make it row 2. And so all that's doing is basically saying I could either write it as this, or I could switch. I could have this one first, now it's second, but again, it's the same solution. So those are the elementary operations that we'll use. And the goal to solve these equations is to take your original augmented matrix, which is the coefficient matrix, and first, to use Gaussian elimination with back substitution, is we want to get it so that we have a 1 here, a 0 here, a 1 there. This can be anything, and the solution is in that little block. And then we can use that value to back substitute to find, once we know this would give us the y solution, then we can use that y to find the x solution, just like we did when we used elimination, like we learned in algebra. So how would we do that? Well, first thing we look for is, are there any rows that have a 1 in the first location? Well, yes, we do. So what I'm going to do is I'm going to use row operation 4, which just says switch rows. Okay, so that's switch rows. Now the next thing I'm going to do is I'm going to add or subtract a multiple of one row from another. So what I'm going to do is I'm going to multiply row 1 by -3 and add to row 2. So row 1 is this. I multiply it that. It just means I multiply each term by -3. So I'll get -1 times -3 is -3. -5 times -3 is 15. 5 times -3 is -15. And then I'm going to substitute it. So I do that, and I'm going to replace. So then I'm going to take that, replace row 2 with new row that I calculated in the previous step. So the new row that I calculated was this thing. Actually, I'm not going to do that. Okay, so I'm going to take, and it says, so I've multiplied it by -3. Okay, so I haven't done the next step, which is I'm going to add that. So I'm going to take this multiple of row 1, and I'm going to add it to row 2, which is 3, 2, 1, 3, 2, 10. So I get 0, 17, -15. Okay, so at this point, I then rewrite the matrix. So I replace the second row with this new thing, which is 0, 17, -15. So what I was trying to get was 1, 0, 1. So I've got it almost there. The only thing I could, if I divide this by 17, this whole row by 17, I'll have 0, because 0 divided by 17 is 0. 17 divided by 17 is 1. -15 over 17 is the answer. So I'm going to say divide row 2 by 17. And then I'm just going to use that new row. So I get 1, -5, 5, 0, 1, -15, 17ths. So at this point, we know that the y solution is -15 17ths. And then we can go back and use back substitution. What that means is I can take this the resulting equation, or the one represented would be x minus 5y is equal to 5. So x, y, constant. And if I solve for x is equal to 5y plus 5. So this goes to the other side, becomes positive. And then I plug in my value y that I've calculated, which is 5 times -15 over 17 plus 5. And what did I just get before, did I? Got -5. I got 5 17ths, not 15 17ths. So let's see if I made a mistake here. Oh, yeah, it's right here. I made a mistake. So when I added these two together, I should have gotten -5 here. So this should be -5. And so that should be -5 17ths. And so y is equal to -5 17ths, not 15 17ths. Okay, now then I plug it back in, -5 17ths. So I get x is equal to -25 17ths plus, in terms of 17ths, that's 85 17ths. I add them together, I get -60 or +60 17ths. So 85 minus 25 is 60. I think that's what I got over here. $60.17. So anyway, you say I got the same answer as I did using elimination. And you're like, well, yeah, okay, that's interesting. Looks like the same answer. some ways that looks more difficult. Well, there's two reasons. When you get to more equations and more unknowns, it's easier to keep track of things when you're just dealing with the numbers. And secondly, this process can be automated in a computer program. So it's something that's transferable to a computer system. So this process of coming down to a matrix, this augmented matrix that has 1, 0, 1, and this giving you the solution, and then using that back is called this Gaussian elimination with back substitution. So, we can do larger matrices, more equations. So let me just make up some equations here. It's x, y, z. What else can I use? Yeah, I'll just do 3. So let's see, plus z is equal to 10 minus 2x plus 3y minus 4z is equal to 5, and 3x plus 4y minus 2z is equal to negative 8. So, there's no easy elimination thing that we can look back into algebra 2, algebra 1 or algebra 2. But what we can do is we can create a matrix representation of this. So we take the coefficients. In any place we don't have a coefficient up front, it's 1. So we get 1, negative 2, 4, or that's 1, sorry. 1, negative 2, 3, negative 4, 3, 4, negative 2. That's multiplied by the solution matrix. That means that's what we're trying to figure out is what the values of x, y, and z are such that all 3 equations are satisfied. And these are the ones that are the constants that are on the right hand side. So that's my matrix. So then what you do is you create this augmented matrix, which is going to be the coefficient matrix, which is this thing. Oh, and I've got to augment it. Like that. And ultimately what we want to do is we want to have 1, 0, 0, 1, 0, 1. And then we have numbers in here. And then we also have numbers over here. And this one will give us the solution for z. We can back substitute into this equation to get the value for y. And then we can back substitute y and z back into this one to find x. So that's where we're going. So the first thing we do is we look to see whether there's any of the rows that have 1 in the first row, which they did, this one, so that's good. Now what we're trying to do is we're going to try to get zeros here and here. So if I multiply row 1, sorry. So we're going to multiply row 1 by 2 and add to row 2. What that'll do is it'll make that go to 0. And I'm going to multiply row 1 by negative 3 and add to row 3. That'll make that go to 0. So let's do that. So row 1 is 1, negative 2, 1, 10, multiply row 1. So we're going to take row 1 and we're going to multiply by 2. So that becomes 2, negative 4, 2, 20. And then we're going to take row 2 plus row 1 times 2. So let's go ahead and write in row 2 here, just so it's over here. So row 2 is, go over here, is that, which is negative 2, 3, negative 4, 5. So we're going to add these two together, and what you get is 0, negative 1, negative 2, 25. Okay, so we're going to substitute that for this row at some point. We're not going to do it yet, though. And the second thing we're going to do is we're going to multiply. So we're going to take row 1 again. 1, negative 2, 1, 10. We're going to make row 1 times negative 3. So we take this times negative 3, this times negative 3, this times negative 3, this times negative 3. So everything here is multiple of negative 3. We're going to then take, then we'll write row 2 down again, row 3 in this case, because we're going to replace row 3. So that's row 3, which is over here. It's 3, 4, negative 2, negative 8. So we add those two together. So what that is it's r row 3 plus row 1 times negative 3. So add these two together, you get 0, 10, negative 5, negative 38. Okay, so we can go back to our original matrix, leave the first row the same. So that's that. And then we take row 3, which is 0, 10, negative 5, negative 38. And because we use these row operations, these two matrices have the same solution. Okay. The next thing we could do is we could take row 2 in the new matrix and multiply by negative 1. So let's just go ahead and do that. And the reason I did that is because I'm trying to get 1, 1 here, and I have 1, negative 1. So if I just change the sign of everything in that row, then now I have 1, 0, 1. Okay, now, so when I do that, I just get 1, 2, negative, I actually get 0, forgot the 0 part, so 0 times negative 1 is 0, 0, negative 1 times negative 1 is positive 1, negative 2 times negative 1 is 2, 25 times negative 1 is negative 25. Okay, so that's the substitution that I use here. And then what I'm going to do is I'm going to use this row to get rid of this term, to make it go to 0. So I'm going to take my new row 2, and I'm going to multiply by negative 10. So here's my new row. So I get 0, 1 times negative 10 is negative 10, 2 times negative 10 is negative 20, negative 25 times negative 10 is positive 250. Okay, then I take that new row 2 times negative 10, so, and I add that to my row 3 from the previous step. So, so let me write row 3 in there. That's 0, 10, negative 5, negative 38. So I add those together. So we get r 2 times negative 10 plus R3. So when I add that, I get 0, I get 0, I get negative 25, and I get 212. So 250 minus 38 is 212. And I substitute that for my row 3. So I get 0, 0, negative 25, 212. And the final step is I multiply row 3 by negative 1 over 25. And what that will do is it will, so that when I multiply these two together, I get 0. Negative 25 times negative 1/25 is 1. And here I get negative 212 over 25. So my final matrix is going to be 1, negative 2, 1, 10, 0, 1, 2, negative 25, 0, 0, 1, negative 212 over 25. So from that final matrix, what I can say is that Z equals negative 212 over 25. From the second equation, I get that Y plus 2Z is equal to negative 25. So I can solve for Y. Y is equal to negative 2Z minus 25. But I just calculated Z, so I get negative 2 times negative 212 over 25 minus 25. So you get the negatives cancel out. 2 times 212 is 424. So I get positive 424 over 25. Then I subtract 25, but that's 25 times 25 is, I get 625, I think. Just finding my calculator. Okay, so 25 times 25 is 625. So this 25 becomes 625 over 25. And then I add the numerators together. 425 plus a negative 625 is negative 201 over 25. So now that's my Y solution. So here's my Z solution. Here's my Y solution. And then finally, the first equation says x minus 2y plus z equals 10. So I'm 1 times x minus 2 times y plus 1 times z is equal to 10. So if I solve for x, that's going to be x is 2y minus z plus 10. But I just found out what y is. It's negative 201 over 25. I subtract z, which z was negative 212 over 25. And then I add 10, but 10 is 250 over 25. So I'll get negative 2 times 201 is 402 plus 212 plus 250, all divided by 25. So 2 times that is that. Negatives cancel out. And so if you have negative 402 plus 212 plus 250, that's 60. So you get 60 over 25, which you can simplify that. If you divide everything by 5, you'll get 60 divided by 5 is 12. So you get 12 fifths. So that's my x solution. So now I have x, y, and z. So that's the whole concept. It takes patience. And I'm just going to pause for a second because I want to see if that's the correct answer. Okay, so there's another way that I'm not going to show you, but that is the correct solution. So that's good. Okay, now what we're going to do is we're going to start here. I'm going to show you how Gauss-Jordan elimination works. So to do Gauss-Jordan elimination, you start with the matrix that you would have had at this point. That we can use back substitution. And the idea for Gauss-Jordan elimination is that you want to come down to this result. And then your answers, your Z answer is here, your Y answer is there, and your X answer is there. So it's essentially doing back substitution just like we did, but it's doing it in matrix form instead of in equation form. So that's the idea. So we have to take our matrix, and first thing we do is we're going to create a 0 here and a 0 there. So what we're going to do is we're going to take row 3 and we're going to multiply by -2. That's so I can eliminate this term. So let's write down row 3 first. So row 3 is one we're not going to change because we've already got that down to the exact thing. So row 3 is 0, 0, 1, -212 over 25. So if we multiply row 3 by -2, you get 0, 0, -2, and -2 times that is positive 424 over 25. So the denominator stays the same, but you just double the numerator and change the sign. Okay, then we're going to take row 2. So here's row 2, which is 0, 1, 2, -25. And then we're going to add those two. So we're going to take row 2 plus row 3 times -2, which are just these two rows. So you add 0 plus 0 is 0, 0 plus 1 is 1, -2 plus 2 is 0, and you add these two together. So you get 424 25ths, and remember 25 times 25 is 625, so you get -625. So when you do that, when you add these together and you find a common denominator, you get -201 over 25. Okay, so and then we're going to do, so let's do that over here. So we're going to keep row 3 the same. So you go 0, 0, 1, -212 over 25. The second row is going to be 0, 1, 0, -20. What did I say it was? 201 over 25. Okay, now we're going to start with row 3 again. 0, 0, 1, -212 over 25. And we're going to take row 3 and we're going to multiply by something. Well, up here you can, comparing row 3 with row 1, all we have to do is change the sign. So I'm going to multiply row 3 by -1. So I multiply this row by -1. You'll get 0, 0. This one will become -1, and this one will become positive 212 over 225. And then I add that, so I'm going to add that to row 1. So I'm going to write down row 1. Row 1 is here. It's 1, -2, 1, 10. So I'm going to draw a horizontal line. And what I'm going to do is take row 1 and add row 3 times -1. So just add these vertically. I get 1, -2, 0, and 212 plus 10. Well, 10 is 250 25ths. So you take 250 plus 212, you get 462. 462 over 25. Okay. So now I'm going to substitute this for row, we've substituted this for row 2. I'm going to substitute this for row 1. So you get 1, negative 2, 0, 462 over 225. So the only thing I have left is I want to get a 0 here. So to do that, I'm going to multiply this row by negative 2 and then add the 2 rows here. So we're going to start off with row 2, which is now 1, 0, 0, 1, 0, negative 201 over 25. I'm going to take row 2 and I'm going to multiply by positive 2. So you get 0, 2, 0, negative 402 over 25. So double the numerator. I'm multiplying by positive 2. Then I take row 1 and just write it down, which is 1, negative 2, 0, 462 over 25. Then I'm going to add these two together. So I get R1 plus R2 times 2. So these are the two, those are the two parts. You add them together and you get 0 plus 1 is 1, 2 plus negative 2 is 0, 0 plus 0 is 0, 462 plus minus 402 is 60, so we get positive 60 over 25, which just can be simplified down to, if you divide by 5, you'll get, what's 60 divided by 5? I should know right off the top of my head. 12. Okay, so we get 12 over 5. So that's just, this is the same thing. I've just simplified the last part. So now the final matrix is going to be 1. For the first row, I'm going to substitute that. So I get 1, 0, 0, 12 fifths. The second and third rows remain unchanged. And so from this matrix, I can say that x is equal to 12 fifths. So that's x plus 0y plus 0z is equal to that. I get 0x plus 1y plus 0z is equal to negative 201 over 25. And then my final answer is the z solution. Z is equal to negative 212 over 25. And you can see that's exactly what I got in the previous step. So that's the whole concept that we're dealing with. We take the original equations, which are multiple linear equations in multiple unknowns. We create a matrix version of the equations. We augment it by combining the coefficient matrix with the constant matrix. In Gauss elimination, we get to a matrix of the form like this, and so that means we can solve for z, and then we take the z and plug it into the corresponding equations. Here, that's back substitution. But if we continue on with the matrix that we can use back substitution, and we proceed to a matrix that is of this form, 1, 0, 0, 0, 1, 0, 0, 0, 1, this column is your solution to the equations. So that is section 8.1.